Okay, thank you very much for this kind invitation, for the opportunity of giving these talks besides online by my side. Okay, well, so essentially I'm going to introduce first some motivation for this mostly really mathematical analysis. And then I will present essentially the results. I will start from all the results that I have obtained with Grasa Carita a few years ago, and then because I think that they are propedeutical to let you understand my more recent contributions related to some results where there are different growth. And those latter results have been obtained, some in collaboration with Cristina Barroso from the University of Lisbon, and the others with Michele Leoteri in University of Modena and Reggio Emilia, and Francesca Prinari at University of Pisa. So, well, okay, the main aim of all this research has been essentially the possibility of giving an integral or at least a measure representation for certain integral functional that arise in connection with optimal design problems or damaging problems. Essentially, the idea is that one has given a functional depending on two fields, chi and u, of the form that you see. Just consider the blue part. So you have this convex combination through a characteristic function of a certain subset of omega that can be or not a subset of finite perimeter. And essentially, according to the phase where you are located, you get different energetical contribution modeled through two bulk energy densities, which are W1 and W0. And then there is this green term that can be considered or not in the analysis. I will essentially going to distinguish what happens in the two cases, which presents essentially a penalization between the interface of the set modeled through chi and its complement. Well, the point is that the WI can have different growth conditions during my talk, and according to that, I will obtain different results. I also want to say that the presence of the green term before is what I was naming perimeter penalization, and as far as I know, the first paper where this term has been introduced mostly for regularity purposes, some old paper by Ambrosio and Buttazzo. While for what concerns the modeling, let's say the blue part, I have to say that it appeared in connection with optimal design in conductivity. And for that, I want to refer to some well-known paper and by Murat and Tartar, but also, let's say, in the mechanical also in the mechanical framework, but there are a list of papers due to Connellin that are to Connestrang that are also, quite important to justify this model. On the other hand, the model appears also in the context of damage. And for that, let's say the model I was presenting is identical to the one that Frankfurt and Marigo have been proposed. So essentially, relating to this latter model, one wants to infimize the energy that I was presenting before. Now I'm not considering any perimeter penalization, as I said, and I'm saying that my bulk energy as this form is the convex combination through chi e of W1 plus k and W0. And the k here stands for the fact that essentially I have a penalization term, in a dissipation term somehow, in the sense that there is a release rate of energy when one passes from a point where there is W0 to one where one has W1. And the point is that for this minimization problem, if there is no convexity imposed on W0 and W1, essentially there is no existence. On the other hand, also, I mean, it's not even in general ensured the existence of a set E. Also because, I mean, if one goes to replace the energy by curly brackets here by its relaxed version in a certain suitable topology, it happens that one starts from characteristics functions chi e, but then one ends, because the only bound is the natural and infinity bound on them, one ends up with a limiting field that can essentially take the entire range of the interval 0, 1. So no longer a set. And that's why, I mean, the importance of having a perimeter penalization. To introduce it, I briefly recall, I mean, my notation, which is, I would say, the standard one, namely saying that whenever I have a field of bounded variation, I mean that I have an L1 field, possibly a vector valued function, such that the distributional derivative is a bounded Radon measure, and I can decompose this bounded Radon measure in three parts. One is the bulk part, whose density I usually will denote by nabla u, and then a jump term, whereby the square bracket u I denote the difference between the half-side Lebesgue limit, tensor the normal to the singular set, and then a diffuse part, a counterpart. So I will say that a characteristic function of a set of finite perimeter is such BV field, and for it, essentially, I will identify the singular set with several symbols that can be, I don't know, S of chi, S of chi e, or even in terms of the reduced boundary, this star E that you see in the end of the slide. And clearly the perimeter of this set E in omega is nothing but the total variation of this chi E. Well, with this notation, the idea is that I want to relax the functional here in black with respect to the L1 topology. But I'm assuming that I have two different bulk densities, W1 and W0, both with the same growth. The same P growth with P strictly bigger than 1. Well, the result that we achieve is the one that is, quite natural to expect, namely that there is no interaction in this relaxation process between the characteristic function chi and the deformation field u, in the sense that we obtain, when I say we again, it's me and Grasa Carita, nothing but the quasi-convexification in the sense of Morey of W1, of this convex combination that I denoted here by capital V. So essentially the quasi-convexification of W1 while we are in E and of W0 while we are in its complement, plus the perimeter term, which is always, which is already lower semi-continuous. So the next question that we addressed was that, okay, what happens if now we start with Sobolev fields, but W1 and W0 have linear growth? So in this case, clearly, so the energy is still the same. The natural topology for which it's obviously automatic to have compactness is again the, let's say, the L1 times L1, or in other words, BV weak stars times BV weak stars for both chi and U. And the point is that because of the fact that V has linear growth in the gradient variable, it's natural to expect that we are ending up in BV, and so there will be an interaction between chi and U. Indeed, the formula that we have achieved is the one that you see in this theorem. let me briefly explain what it is. And it's again the bulk energy that I was having also before in the Sobolev setting, plus its recession in the counter part of U, of the gradient of U. And of course, okay, here I'm using the same symbol for a field and its precise representative, plus a surface term that I'm denoted here by capital K, depending on the 12th limit of chi of U and the normal. I will clarify in a moment what I mean by this normal and why I'm just having a normal. Because, okay, first of all, let me say that chi is given by a formula which has memory of the fact that chi is truly an SBV field. So essentially, I'm infimizing on fields of the same type, while U has erased as a limit of Sobolev fields. So I am infimizing my this energy here in brackets, so the QV infinity plus the perimeter of chi on this class, where I mean Q nu represents a cube which has one side parallel to nu and all the others clearly orthogonal. So this K can be actually specialized in the sense that according to the fact that I may have along the interface generated by the singular set of the couple chi U, I may have either just chi jumping, and in that case, K reduces to the total variation of chi, or I may have just U jumping, and in that case, I'm still left with the recession function of the quasi-convexification of V, or really if both jumps, I really have the interaction between the two terms, and K as this strange formula. Well, for the proof, and let me briefly mention that, I have to say that the tricks that we have been used are so far quite standard. So we were adopting blow-up techniques and clearly making a lower bound estimate for the diffuse part, neglecting the perimeter contribution in the original density, in the original energy, while clearly for the upper bound, it was crucial to prove that calligraphic F is indeed a measure, and a measure which is absolutely continuous with respect to the Lebesgue one and the total variation of chi and U. Okay, then just for the jump term, we were in need of really a direct estimate. What's the point? Okay, this is actually what happened in the case where W0 and W1 have the same growth, are different energy but with the same growth. It becomes more interesting the case where essentially W1 and W0 might have different growth. For instance, I don't know, W1 with a certain Q growth and W0 with a P growth with P different from Q, possibly smaller. And the point is that one needs somehow to understand what happens to the relaxed functional. Because what's the point? The point is that one has more regular functions, let's say UN are in W1Q, or in a, let's say in a wider context are W1Q log of A. But on the other hand, because of some structure hypothesis that I was briefly mentioned, let's say that one of the two energy has, for instance, P growth, then the compactness happens to be in W1P weak. So the point is that, okay, while for the perimeter, as I was emphasizing here in the last line, there is no difference with the previous analysis. So here the situation becomes much more complicated or less standard than in the previous setting. And the point is that indeed there is the so-called gap between the fields that we are using to approach our relaxed energy and the sets where possibly this relaxed energy might be finite. And so the crucial part is that one wants to understand if it's really possible indeed to approximate fields which are in W1P by those who are in W1Q. And okay. So the problem in itself, without the chi component, let's say, so without any difference between the two phases, so just with an energy density little f here in blue, which might have different growth from above and below, has been addressed by many authors, but let me say the following, that clearly, I mean, if there is no gap between P and Q, we end up to the famous result by Acerbi Fusco. Otherwise, if there is a big difference between P and Q, it might even happen that the F here, let me go to the 2 slides before, might not even be a measure or might be 0 over certain fields. So clearly, I mean, the idea is that when our F before or F lock before are really measures, and what can we say about their representations? Essentially, the idea is that we want to give kind of weak or strong representation according if our field are in W1Q or W1Q lock. So let me say that I can say that a measure mu, a radon measure mu, represents a certain functional here denoted by calligraphic G if mu A is equal to this functional calligraphic G, or I will talk about weak representation if essentially G is in between mu of A and mu of the closure of A. Morally, that some concentration, somehow effect appears at the boundary of A. And this happens clearly for every open subset A in the given omega. Well, for what concerns the literature, in the case, in the truly Sobolev case, so when P is bigger than 1, and Q is in between P and N over N minus 1 times P, Fonseca and Mali have proven that the functional the functional FQP or FQP lock, according to where UN here is, admits the first a weak representation and the second a strong representation. So essentially, a radon measure exists. It's quite complicated to predict how this measure looks like. And in fact, there have been, after this famous paper, several results in several contexts. For sure, what can be proved is that this measure mu can be represented by the quasi-convexification, again in the sense of Morrey, of the density F. Here I have written a lower bound, but actually equality can be proven. But it's not obvious if this is the only part of this measure, namely if mu is just Lebesgue, is just a Lebesgue type measure. And in fact, in some particular case, some counterexample have been given to the fact that this measure is just a bulk type. Well, also I want to say that the analysis for the case P equal to 1, for the sake of completeness, let me say, has been addressed first by Christensen and then by his student Personaggi, and again, just a lower bound to the relaxation of, let's say, FQ1 lock has been provided in terms of the quasi-convexification, while something else has been obtained in inhomogeneous case in the Sobolev setting, so namely p bigger than 1. And sorry, there is a typo in the first line because Christensen have addressed also the case p equal to 1. I apologize for this imprecision, but okay, let me go back to what I was saying. In the case where there is inhomogeneity and the density H, the original density H is convex. Well, in that case, Acerbi, Buscitti, and Fonseca have proven that FQP log is indeed a measure which has as bulk part H itself, as it is natural to expect, plus a singular measure mu, which is singular with respect to Lebesgue. And the point is that not much better can be done. And in fact, the same analysis has been then somehow extended under certain assumptions by Mingione and Mucci, still in the Sobolev setting. And in fact, they have proven that there is just a bulk measure under a suitable continuity assumption in the X variable on the original density F. So considering the same problem as Fonseca-Mali, but having PQ growth, but moving, let's say, from the P growth to the Q growth in a regular way, then the relaxed functional is just the quasi-convex envelope of F, while if this is not the case, actually the model obtained in the convex case by Acerbi, Buscitti, and Fonseca is sharp. Essentially, there is the appearance of a singular measure. Well, okay, so somehow, let's say the modeling appears in the Ogden materials case, where one has a truly polyconvex energy, is not covered by Mingione and Mucci because indeed there is really, let's say, a gap in the growth, and there is no smooth passage from the P and the Q part. Well, okay, and in this context, our analysis, mine and with Anna Cristina, have been obtained. Essentially, again, having in mind the original problem coming from the damage, we started by relaxing this energy in red in the last line, with considering either fields UN in W1Q or in W1Q log. And the point is that it's possible to prove that there is a weak representation for this measure, as it was in the case with no chi dependence. And also, let's say, we are able, in fact, to let's say, to prove that we can say something even better in some specific case. Okay, so essentially we were first imposing coercivity condition, but then even the coercivity condition can be removed. The key idea in our, the key tool, let's say, in our analysis relies on a previous result by Fonseca-Mali in the case with no chi, essentially the possibility of gluing two W1P fields in a suitable layer where there is an increasing summability, namely a W1Q. And this is essentially the Q point to control the energy. On the other hand, in the case where the fields are W1Q lock, we can say better. So we can essentially explicit which is our bulk energy in the case of W0 and W1 are convex, and we recover somehow the Acerbi, Buscitti, Fonseca result. But our representation indeed is not so nice. Why is not so nice? It's not so nice because we had the appearance of this singular measure μs, but this S stands just for the fact that mu can be singular with respect to the bulk energy here expressed by V, the first integral. But in principle, we cannot exclude that this measure concentrates in the singular set of chi. So we were trying to understand if it's possible to detect at least a certain class of chi where this measure does not appear. And the fact is that this was indeed possible. Okay, let me also saying that this is possible. Surely in the case where we are in dimension 1, also because, and this is somehow this result gives an hint of which are the tools also for my next result, the result that I'm going to show in a while, is that essentially even, for any P and Q, if we are just in R, essentially we are able to approximate chi by other sets of finite perimeter, all contained inside the given set chi. And essentially there is no singular measure appearing in this relaxation procedure. And because of the one dimension, we can get the convexity just in the last step, let's say via relaxation procedure. But so we can neglect the convexity assumptions at the beginning. On the other hand, what happens in more dimension? In more dimension, we can somehow select a class of sets chi as it always happens in dimension 1. So we are going to select a class of sets which have been studied by Thomas Schmidt. And essentially, those are sets that can be approximated from inside by smooth sets. In such a way, also the perimeter converge. And this is clearly important because if you have in mind the original model, we have, let's say, a part of our body where we have P growth modeled by W0 and another part in the complement where we have Q growth. So clearly, if the approximation does not appear made by being always inside either one set or its complement, then clearly we cannot control the approximating energy. So the result by Schmidt indeed says the following, says that if I have a bounded open set E for which essentially there is no difference in the sense of the Hausdorff measure between the reduced boundary and the topological boundary, then it's possible essentially to approach E by a sequence of sets that here are denoted by E epsilon, such that the difference between E and the epsilon are contained on an epsilon neighborhood, or the intersection of the epsilon neighborhoods of the boundaries of E and the epsilon. And also, there is this control on the perimeter that morally says that in the end we have convergence of the perimeter to the perimeters, so morally strict convergence in BV. So, and in fact, is what I was saying. And also, it happens that, of course, there is L1 convergence of the characteristic function of E epsilon to the characteristic function of E. Of course, there are a wide class of sets for which this happens, and in this class there are Lipschitz sets. But on the other hand, it's also very easy to consider examples of sets like the set E here, which is 0, 1 to the power n minus 1 times the interval 0, 1 without the half line, where essentially all the inner approximation have just satisfied the classical inequality, but in a strict way between the perimeters. So, and in fact, for these sets, our representation we expect that is going to fail. So let me recall again that we can consider of having two densities, maybe without even imposing any coercivity as I am considering here. So W1 with growth P and W0 with growth Q. Then here I consider, as usual, by capital B, I denote the convex combination. Assuming that V is convex, namely W0 and W1 are convex, and if I consider a set chi for which both the the reduced boundary of E and of the complement of the closure of E in omega satisfy the Schmidt assumption, then whenever I have a field U in W1P, such that clearly I have better summability in the complement, then both F lock and F don't have any singular term in their integral representation. I wanted to say that this assumption here in blue, the fact that I'm assuming that U is W1Q in the complement of E bar, is also quite natural, because of course we want to represent the energy when it is finite, and if I assume that I have a control of a certain type, clearly I'm expecting that on a certain area, in a certain region of omega, I really have this Q growth behavior on the gradient. Let me say that without being so precise, so without these restrictions of chi, other tools can be used, for instance, those introduced by Christensen, who was making use of the so-called closed W1P quasi-convexity, a notion introduced by Pedregal, namely saying that for function that may even take the value plus infinity, the Jensen's inequality with respect to homogeneous W1P gradient Young measure are satisfied, this inequality and in red. Then for this class, clearly one has lower semi-continuity of the original function. The point is that this result is not completely satisfactory, because somehow allowing the fact that our energy can take the value plus infinity, we are unable to say where our relaxed functional is indeed finite or not. So, I mean, it's a morally a formal result, but not really giving explicit information about the finiteness. And that's why we were at least restricting the sets of chi and obtaining the previous results. On the other hand, one might ask, okay, but if you stick to the Sobolev setting, essentially you are very close to the analysis performed by Mingione and Mucci. But well, the answer is indeed no. Because, okay, it's true that our density V, the capital V before, can be identified with such an H here, depending on X and the variable psi, which stands for the gradient, and who has a certain px growth, because clearly it depends on X. But this px growth for us is nothing but a convex combination of P and Q, assuming that, for instance, W0 is the power, I don't know, psi to the power Q, and W1 is psi to the power P. This Px is now a convex combination through a characteristic function of P and Q. So no way of adapting those results where are really exploiting the continuity of Px in X. That, of course, we don't have. Also, let me say, due to and then, I mean, I hope to have a few minutes to connect with the analysis made by Mingione and Mucci, introducing another class of problems. Essentially, okay, one of the reasons for which these optimal design problems are interesting is that essentially from the mechanical viewpoint, they model the so-called worst optimal design, and this is also important to model thin structures. So one could consider an elastic membrane or an elastic string, namely there is a 3D, 2D dimension reduction process where one replaces the original set omega by this Cartesian product between omega and 0 epsilon, or one consider a fixed length 0L and then multiplies by the ball in R2 over center at the origin and with radius epsilon. And then the idea is that one wants to minimize these energies here, assuming that, for instance, one has a set at least of this cylindric type, E times 0 epsilon, if we are in the 3D, 2D dimension reduction setting. And also, I'm sorry if I neglected this aspect before, but I can comment it later. One can assume that there is a prescribed volume fraction of the set chi. I was neglecting this aspect before because one way of dealing with this term is maybe introducing a Lagrange multiplier instead of considering a precise volume fraction, and having a Lagrange multiplier from the perspective of the relaxation doesn't imply any change in the analysis. That's why I was neglecting. Anyway, let me say that in the 3D, 2D dimension reduction, knowing that the quasi-convexification is indeed a convexification and imposing a certain coercivity, then for also prescribing a lateral boundary condition on our domain, we can say that among fields which are, of course, W1Q in the complement of E and W1P otherwise, we have a representation where clearly of this energy here. So we are able to consider this integral representation here given by equation 3, which essentially is equivalent at studying the problem I was mentioning before, because after a rescaling of epsilon, the infimum here, I'm sorry, this one is equivalent at infimizing this energy here with this change of variable. And and then one obtains, let's say, what one expects, namely the appearance of the quasi-convexification of V hat, where V hat is the energy that one achieves infimizing with respect to the last variable of psi, let's call it psi3, namely because this term 1 over epsilon and the derivative with respect to the third variable of u epsilon is expected clearly to disappear due to the natural compactness. The same results holds in dimension 1, so essentially for elastic strings, and one recovers the classical, let's say very classical, because it goes back to Acerbi, Buttazzo, and Percivale, essentially obtaining the convexification of the V0, where V0 is now the infimum with respect to the first two variables of the derivatives of U and the perimeter. I don't want to say anything about the proof. Let me just say that this result that we have achieved with Anna Cristina clearly covers now the case of piecewise constant Sobolev exponent. So we are in the case of a variable exponent with a piecewise constant. And the natural question is that what happens, if really there is not just a control, but we have really P growth from one side and Q growth from the other. And well, again, the results is the same that I was presenting before, namely the functional, the relaxed functional here is given by what one expects, essentially no singular measures appears on limiting set chi who have the properties of being of Schmidt type. Of course, there is a slightly different analysis, let me just say that, because of course here, assuming that there is completely a region where we have Q growth and another where we have P growth, this requires to make a very good approximation, but okay, this is still, let's say, possible. I don't have time to enter the details of the proof. But then the point is that, okay, what happens if now we go back somehow to the analysis by Mingione and Mucci. So namely, we consider a generic PX now, where this PX is smoothly depending on X. So no longer a convex combination through a set of finite perimeter. Okay, the problem has been solved already by Mingione and Mucci in the sense of the relaxation, assuming that we have enough regularity on this exponent px. But our aim, mine and Michela and Francesca, Michela Elvira and Francesca Plinari, is the case of dimension reduction. Because the case of dimension reduction, due to the fact that we have a rescaling in the variable, affects the exponent p here. So we have no longer a fixed exponent, but somehow a family of p epsilon converging exponents. So we are still able to achieve an integral representation result under this assumption. So we assume essentially that we have a Carré-Theodori type energy W, and we assume that W has linear growth, and we consider that making a transverse rescaling, this affects the exponent px to become p of x alpha and epsilon x3, where x alpha stands for the planar variable in little omega. Then, if we consider our energy here, its relaxation in this, let's say L1 strong convergence for the fields U becomes the quasi-convexification of W hat to the power P0, where P0 is nothing but the limit, the uniform limit of the P epsilon. This is somehow a stronger assumption, one can say, requiring that P epsilon goes uniformly to P0. But if one considers the model and thinks that P epsilon is nothing but a rescaling of a certain P, and one requires that the P is enough regular, let's say, is of a P log type, then it naturally goes to a P0, which is nothing but P at x alpha and 0. So somehow the assumption is not too bad. And the other thing is that via compactness, and this was somehow requiring, our analysis, is that we have fields U epsilon which lives in different Sobolev space, but then we are able to prove that the target, the limiting field, lives in W1 P0. Okay, here I am assuming that the functions are clamped in the lateral boundary, and so clearly, okay, the limiting field will be clamped as well in the little omega. The same result can be extended, let's say the same type of result can be extended considering a product type dependence on X, not of power type, so essentially multiplying our W by an A of X alpha and X3, and still the same type of result can be obtained. More, let's say, weaker assumption can be imposed on W, can be imposed on the convergence of the exponent, provided that W is indeed convex in the gradient variable. And this because, of course, for the lower bound, one can always apply Joffre's theorem. And I stop here. I hope I didn't take too much time. And I thank you for your attention.
Thank you very much. Here on the screen, maybe. So, are there? Thank you very much, first of all. And are there any questions?
Hi, Elvira, I'm Elisa. Maybe just a very quick question about the second result that you talked about, the one with Anna Cristina.
Yes.
Could you also have sequence of energies without, say, coercivity growth from below? I'm asking because I'm thinking to the case of these double porosity materials, because in that case, if you could also treat sequence of energies, you would get, as special cases, those homogenization results, right?
Yes, but I guess that, okay, let me say, we are considering any way of having W1P, convergence. So even if, let's say, it's not really impose the coercivity, the topology that we are considering is anyway W1P, let's say. So also because, due to the fact that there is always, even, let's say, even without chi, if I'm understanding your question, even without chi, you might end up with limiting function, or let's say relaxed function, which are no integrals otherwise. So anyway, you have to impose that you have convergence in a sub-F field, in a sub-F space, which is close to the sequences. So if they are W1Q, the convergence has to be not too far from being weak W1Q, so W1P with P suitably close to Q.
Okay, thanks a lot.
So not really in the densities, the coercivity, but for the convergence, something you need.
Okay, thanks.
Further questions? Then I maybe have a question, maybe not directly to the elasticity part, but to the approximation of the set E, okay, where you of the Schmidt result, I think. Proof just the we approximated where you, what was that, the Hausdorff measure of the reduced boundary is equal to the perimeter, I think, and then just the proof if that is constructive in some way, if one could be constructing, I mean, constructing in the way, if I would like to approximate that in some way.
Let me go there. I'm trying to go there if I'm understanding, to understand better your question. I don't know why I cannot just click back where it was here. Or maybe, let's see here. Do you want really the approximation? Okay. This, okay. Yes. Please.
Just the EAPs, I mean, they exist, the open EAPs? I mean, just the proof, I mean, not the proof now, but is the proof constructive, or is it just, okay, they exist, just exist this, I mean, this would just...
No, it is somehow, let's say, constructed, because as far as I remember is that it's really used somehow the flatness of the boundary of the set T. So it's really modeled. You somehow know up to a certain error how E epsilon looks like. So it's really made in terms of certain distance from the boundary of E and so on. So really the construction is made. It's not just an existence result, I would say.
Okay.
So you may say how it is. I also think, because of another question, that there are persons interested nowadays in understanding if the approximation can be also in the sense of curvature. But I mean, I was never really entering into that. So really, I mean, it's a construction made by hands.
Okay, thank you very much. Okay, further my last question. Further questions in the audience? Not. We would like to thank you also. Yeah, we would like to thank you, and yes, also that you could still make it online. I mean, we are very grateful.
Yes, I mean, after five doses of vaccine, at least it was quite weak, the COVID, but still, okay. So thank you.
Yeah, thank you very much.